Hello guys, welcome back to my channel Algorithm Avenue. From our past few videos, we have been discussing about the different techniques to improve the performance of an artificial neural network. So in this video, we'll be discussing about another important topics, that is weights initialization, which is a technique which can boost your performance of an artificial neural network. Okay, now in this video, we'll be discussing about the weights initialization technique in detail. Okay, now this entire weights initialization topic is divided into two parts. Okay, in the first part we'll be seeing how not to initialize the weights. Okay, how not to initialize the weights, not to initialize the weights. And in the second part we'll be discussing how can we initialize the weights. Okay, that means different types of techniques. Okay, different types of techniques to initialize the weights. Okay, now in this video we'll be discussing about how not to initialize the weights. Okay, now before going into the discussion, let us see what is the importance of the weights and bias in an artificial neural network. So to understand this, let us see how an artificial neural network basically works. Okay, now artificial neural network works in three steps. Okay, first we initialize the parameters, and second we choose optimization algorithm. Now in the third step we'll be having this entire four steps. Okay, first we forward propagate the input and calculate the cost function between the predicted output and true output, and second we'll be computing the gradients with respect to the parameters. Okay, we'll be calculating the derivative of loss with respect to the parameters in the back propagation step, and then we update the parameters by weights and bias updation rules. Okay, this is how an artificial neural network basically works. Okay, now when you observe these steps, we can clearly see that the first step is the most important step. Okay, now why it is said that the first step is most important is, now what are the two numerical values that we pass through an artificial neural network? First is data and second is parameters, right? The data cannot be altered. Okay, it is constant value. The only thing that can be altered is parameters. Okay, now these parameters will entirely determine the output of an artificial neural network, or it may be output of the nodes. Okay, each of the numerical value, okay, each of the numerical value, whether it may be gradients or it may be the output of an node, okay, is determined by this parameters. So proper initialization of the parameters is very much important. Okay, so that is why it is said that initialization of the parameters is the most important step in an artificial neural network. Okay, so we have understood the importance of initialization of the parameters. Okay, now we'll be discussing the disadvantages of wrongly initializing the parameters. Okay, the first disadvantage that comes is vanishing gradient problem. Okay, this is the most frequent problem that we face in an artificial neural network, and one of the cause of this vanishing gradient problem is initialization of the parameters. Okay, and the second is exploding gradient problem, and the third is slower convergence. These are the three frequently faced problems by the wrongly initialization of the parameters. Okay. Till now we have seen that weights and bias being initialized to 0, or weights and bias being initialized to some random value. Now our aim is to prove that these techniques are entirely wrong. Now let us discuss our first case where we initialize weights and bias parameters to 0. Okay, now when you clearly observe this neural network, we have several weights and bias parameters, right? Now the entire weights and bias parameters in this artificial neural network are initialized to 0. That is, weights is equal to 0 and bias is equal to 0. Okay, now let's start our discussion by taking weights and bias values as zeros. Okay, now I'll be talking with respect to both these nodes. Okay, now with respect to this node, when I calculate weighted sum z11, it corresponds to w1 x1 plus w1 x2 plus b1. Right, now when you calculate this node output, that is weighted sum z12, it corresponds to w1 x1 plus w1 x2 plus b1, right? Now what we will be doing is we'll be taking three cases. Okay, in this we'll be taking three sub cases. First we'll be applying relu activation function in the hidden layers, and second we'll be applying tanh activation function in the hidden layers, and third we'll be applying sigmoid activation function. Okay, first we'll be taking relu activation function. Okay, now we are considering relu activation function, and we'll be taking activation function output of this node as a11. Okay, a11 is equal to maximum of 0 comma z11, right? This is what relu activation function specifies. Now we'll be calculating a12, that is maximum of 0 comma z12. Okay, now first before calculating this activation function outputs, we need to determine z11 and z12. Okay, now let's calculate z11. Okay, we have already seen that we initialize weights and bias to 0. Okay, now this entire weights, okay, this entire weights and bias are 0. Okay, now this entire term becomes 0, this term becomes 0, and this term becomes 0. So this entire z11 value is equal to 0. Okay, now similar with the case of z12, so it becomes 0. Okay, now we'll be passing this z11 and z12 through relu activation function. Okay, now let's take activation function of this node, that is a11, that is maximum of 0 comma z11. Okay, what is z11? Z11 is 0. Okay, what is Z12? Z12 is 0. Okay, now when it comes to A11, maximum of 0 comma 0. Okay, what is maximum of 0 comma 0? It is 0. Okay, now let's calculate A12. A12 maximum of 0 comma 0, that is 0. Okay, now the activations are 0. Okay, now the derivative of this activation functions with respect to z11 and z12 are also 0. That is, dou a11 by dou z11 is equal to 0, and dou a12 by dou z12 is also equal to 0. Okay, now when these derivative values are 0 at the time of gradient calculation, okay, at the time of gradient calculation, when we update the weights, we do gradient calculation. Okay, we do gradient calculation, right? Now this is the gradient. Now at the time of gradient calculation, these derivatives are involved. Okay, at the time of gradient calculation, these derivatives are involved. So when these derivative values are involved, as the derivative value is 0, this entire term becomes 0. Okay, similar in the case of this node output. Okay, now when this value becomes 0, this entire term, okay, this entire term becomes 0. Okay, now when this entire term is 0, w new value is equal to w old value, means previous weight value and newly updated weight value are equal. Okay, when both these weights are equal, we have seen that problem of dying relu. Okay, we have already clearly discussed about the problem of dying relu. Okay, what is dying relu? The inability of the activation function to update the weights and bias parameters. Okay, the inability of the activation function, okay, relu activation function, to update the weights and bias parameters. Right, now here you can see that w new value is equal to w old value, where we taken relu activation function. Means when we take in relu activation function, as both these weight values are equal, means the node is dead. Okay, the node is dead. Once the node is dead, it is dead forever. Okay, once you have initialized the weight values, those those initialized weight values will continue forever in the training. Okay, let's say you have taken 100 epochs for training. Once you initialize the weight values as 0, that 0 weight value will continue till the end of training. Okay, till the end of training, the weight value, okay, the weight value is 0. Means the model is not learning anything. Okay, model is not learning anything, so it cannot make any predictions. Okay, it cannot make any predictions on the future data. Okay, this is the problem with relu activation function. Okay, when the weights and bias values are initialized to 0. Okay, now let's discuss with respect to tanh activation function. Okay, the tanh activation function also behaves similar to relu activation function. Okay, the only change is the formula. Okay, in tanh activation function, we'll be having e power z11 minus e power minus z11 by e power z11 plus e power minus z11. Okay, this is the tanh activation function formula with respect to, okay, with respect to f of, let's say, z1. Okay, now I have chosen z11, okay, this node, so I have written with respect to z11 the formula. Okay, now as we know the value of z11 is 0, so what is e power 0? It is 1. Okay, now what is e power minus 0? It is 1. Okay, 1 minus 0, sorry, 1 minus 1, it is 0, right? Means the, sorry, the tanh activation function is also producing 0 output when the weights and bias values are initialized to 0. Okay, similarly what we have seen in relu activation function, the similar thing we are seeing in tanh activation function as well. Okay, so the entire problem is same, means weights and bias will be equal till the end of the training. Okay, model will not learn anything, it will not be able to find the any complex patterns in the data set. Okay, the entire model becomes a linear model. Okay, this is the case when we use relu and tanh activation function. Okay, only the sigmoid activation function acts little different. Okay, now we'll be discussing the sigmoid activation function in detail. We have seen the case one for relu and tanh activation functions. Now let's discuss with respect to sigmoid activation function. Okay, now before discussing with respect to sigmoid activation function, I want to specify a small change in the neural network. That is, the notation previously was specified as w121, but it is changed to w112. Okay, here in the formula as well we have changed it to w112. Okay, this is the only change that I have made in the neural network. Okay, now let's discuss with respect to sigmoid activation function. Okay, now this is the z11, that is the output of this hidden unit, and this is z12, that is output of this hidden unit. Okay, I'll be considering only this both hidden units. Okay, now let's say this output, okay, this output that is weighted sum is passed through sigmoid activation function. Okay, the activation function output of this hidden unit is represented by a11, the activation function output of this hidden unit is represented by a12. Okay, now we need to pass this weighted sum, okay, that is the output of this node, through sigmoid activation function. Okay, sigmoid activation function. Okay, what is the formula of sigmoid activation function? 1 by 1 plus e power minus z, right? Okay, in place of z what we have over here? Z11, so it is replaced by z11. Okay, but what is the value of z11? It is 0. Okay, the z11 value is 0, so 1 by 1 plus e power minus 0. Okay, what is the value of e power minus 0 or e power plus 0? That is 1, right? So 1 by 1 plus 1. Okay, 1 by 1 plus 1, that is 1 by 2, so this comes out to be 0.5. That is, the entire output of this node applied sigmoid activation function is 0.5. Okay, similarly when we calculate with respect to this node, the output will be 0.5. Okay, this is how we calculate the activation function outputs for both the hidden units. Okay, now after calculation of the activation function outputs, we need to find out derivatives, right? Okay, we need to find the derivatives. Now dou a11 by dou z11 is equal to, what is the derivative of 0.5 with respect to z11? It is same, 0.5. Okay, similarly we need to calculate the derivative of this a12, dou a12 by dou z12, this is also 0.5. Okay, now after calculating these derivatives, we need to calculate the value of gradients. Okay, we need to calculate the value of gradients. Why we need to calculate the value of gradients? To update the weights and bias. Okay, while we update the weights and bias, that is w new is equal to w old minus learning rate dou L by dou W. Okay, this is the value of gradient. Okay, this is called gradient. Now we need to calculate gradients with respect to these four weights. Okay, we need to calculate gradient with respect to with these four weights. Okay, why we are calculating with respect to these four weights? Because we are taking only these two nodes. Okay, as we are taking only these both hidden units, we need to calculate the gradient with respect to these four weights. Okay, now at the time of gradient calculation, these values are involved. Okay, now let us calculate. Okay, first let us calculate the gradient. Dou L by, okay, dou L by, what is the first weight? W1 1 1. Okay, now this comes out to be the back propagation chain. Okay, we need to expand this gradient in the form of back propagation chain rule. Okay, now this comes out to be dou L by dou y hat into y hat is dependent on dou y hat by dou a11, and dou a11 is dependent on z11, and dou z11 is dependent on dou w11. Okay, this is the gradient expansion of this weight. Okay, now we need to calculate the similar for this weight. Okay, dou L by dou w1 12 is equal to dou L by dou y hat and dou y hat by dou a11 and dou a11 by, sorry, it is a12, and this is also a12, dou z12 into dou z12 divided by dou w112. Okay, now let's calculate the similar gradients for both these weights. Okay, now dou L by dou w121 is equal to dou L by dou y hat into dou y hat by dou a11 and dou a11 by dou z11 and dou z11 by dou w121, right? Now with respect to this weight, dou w122 is equal to dou L by dou y hat into dou y hat by dou a12 and dou a12 divided by dou z12 into dou z12 divided by dou w122. Okay, these are the four gradient values. Now if you keenly observe each gradient value, you see that first, when it comes to initial observations, both these derivative values are similar in all the gradients, right? Okay, both these gradient values are similar. Okay, why they are similar? See, a11 value is equal, right? A11 value is 0.5 and a12 value is 0.5, means both the values are equal, so this entire derivative will be same. Okay, so these both derivative values are equal. Now let's see this third derivative value. See, here we have a11 is equal to a12. Okay, a11 is equal to a12 and z11 is equal to z12. Okay, 0 0, so z11 is equal to z12 and 0.5 0.5, a11 is equal to a12. So these entire three derivative values, okay, these entire three derivative values are equal. Okay, these entire three derivative values are equal. Now the only change comes in this gradient calculation is this part. Okay, the only change that is made is this part. Now let's calculate with respect to this w111 and w112. Okay, now let's take this first case. Okay, let's calculate for this derivative value. Okay, let's calculate for this derivative value. Now I'm finding the derivative with respect to w111, right? Okay, what is z11 value? Z11 is equal to this entire equation. Okay, z11 is the entire equation. Now I am finding the partial derivative with respect to w111. Okay, now I'm calculating the partial derivative with respect to w111. So these both values will be 0. Okay, these both values will be 0 and I'll be getting this as x1. Okay, now let's take this z12. Okay, z12, and I'm finding the partial derivative with respect to w112. So this entire part will be 0 and this part will be 0. Okay, these both these terms will be 0 and I'll be left out with x1. Okay, I'll be left out with x1. Now similarly, while I calculate with respect to w121 with z1, sorry, z11, this term will be 0 and this term will be 0 and I'll be left out with this term, that is x2. Okay, similarly here I'll be getting x2. Okay, now both these derivative values are equal. Okay, both these gradient values are equal, and both these gradient values are equal, right? Both these gradient values are equal, and both these gradient values are equal. Okay, now we have seen that both these set of gradient values are equal. Now, as the weights initialized are equal, okay, as the weights initialized are 0, right? We have initialized 0 weights. Okay, now from this 0, okay, from this 0 I'll be subtracting this term, right? I'll be subtracting this term. Okay, that is learning rate multiplied by this gradient value. Okay, now when I subtract this term, I'll be getting some numerical value. Okay, I'll be getting some numerical value. Now, with respect to this weight, okay, I have got a numerical value for this weight. Now I'll be calculating with respect to this weight. Now when it comes to this weight, I'll be initialized with 0 weight value, and I'll be subtracting some learning rate into gradient value. Okay, what is the gradient value? Equal to this gradient value. Okay, this gradient value is equal to this gradient value, right? So when the gradient values are equal, I'll be getting both these updated weight values. Okay, both these updated weight values same. Okay, this w111 new and w112 new are equal. Okay, similar goes with this w121 and w122. Means these values, okay, both these weight values and both these weight values, okay, both this set of weight values are same. Okay, are same for the entire training process. Okay, not only just one epoch, even if you train for 100 epochs, the entire weight values, okay, w11 and w112 are always equal. Okay, are always equal, and w121 and w122 are always equal. Okay, so when this equality follows, what actually happens is, what your neural network assumes is, okay, after certain training, what your actually neural network assumes is, it transforms the architecture in this form. Okay, it what the neural network considers is, it considers both these weight values as a single weight value. Okay, as these weight values are always equal in the entire training process, what it assumes, it assumes these both weight values as single weight value, and these both weight values as single weight value, and it transforms this entire hidden unit, okay, entire two hidden units into single hidden unit. Okay, so the architecture get transformed into this form. Okay, architecture gets transformed into this form. Even if you had 100 hidden units, okay, if you could have 100 hidden units, it transforms the entire architecture into this form. Okay, this is the main disadvantage of having weights initialized to 0 and using sigmoid activation function in the hidden layers. Okay, no matter of how many hidden units you have, the entire architecture gets transformed into this, because the weight values are similar. Okay, the old weight values and updated weight values are similar in the entire training process. Okay, so this is how sigmoid activation function and weights initialized to 0 affects the performance of an artificial neural network. The entire model becomes a linear model. Means the model will not be able to find the non-linear patterns in a data set. Okay, so in this case, what actually happens is, the model will not be able to find the non-linear patterns in the data set. Okay, this model becomes a linear model. Okay, this model becomes a linear model. It can only find the linear patterns but not the non-linear patterns. Okay, this is the main disadvantage of using sigmoid activation function with weights and bias initialized to 0.
I've
Okay,
seen that by initializing the weights and bias values to 0 and using different activation functions in the hidden layers, our model becomes an linear model. Okay, now what we will be doing in this section is, we'll be taking a dataset. First we'll be training this dataset on a normal model. Okay, what is meant by this normal model is, which has relu activation function in the hidden layers and weights and bias values initialized by the scikit-learn library. Okay, now first we'll be training our dataset on a normal model. Okay, for that I'm importing the necessary libraries and my dataset, that is make circles dataset. I'm taking 1000 samples and storing all the features in X and target variable in Y, and this is my dataset. Okay, which contains red and blue as my labels. Okay, now I'm splitting my data into training and testing. I'm giving 80% of the data to training and 20% of the data to testing. Okay, after that I'm converting from numpy to tensors. Okay, and this is my model with relu activation function, and this is my loss function, that is BC with logits loss, and my optimizer is Adam optimizer, and this is my accuracy function, and I'm training for 100 epochs, and this entire part is my training loop, and this entire part is my testing loop, and I'm printing my results. Okay, as I have larger data set trained over a smaller model, I have got around 55% training accuracy and 51% test accuracy. That means model is learning something. Okay, model is trying to learn something. Okay, now what we will be doing is, okay, this is my these are my model weights and bias values. Okay, these are my final model weights and bias values. Now what we will be doing is, we'll be initializing the weights and bias values to 0 and take different activation functions in the hidden layer. Okay, first we'll be initializing the weights and bias values to 0, and we'll be taking relu activation function in the hidden layers. Okay, now this is my model. Okay, this entire part is my model with relu activation function in the hidden layer, and then what I am doing is, I'm picking each layer. Okay, I'm picking each layer in this for loop. Okay, in this for loop I am picking each layer and initializing the weights and bias values which are linked to that layer to 0. Okay, you see that I have initialized all the weights and bias values to 0. Then I have considered the loss function and optimizer, and this is part is my training loop, and this part is my testing loop. And you see that after 90 epochs, okay, after 90 epochs I got around 50% training accuracy and 50% test accuracy. Means what actually is happening, your model is trying to predict either 1, okay, either 1 for the entire data set or either 0 for the entire data set. Okay, it is just randomly guessing that I'll be printing 1 for the entire data set. Okay, how many rows of data you give, I'll be printing 1. Okay, how many rows you give, I'll be printing 0. Okay, either it is printing 1, either it is predicting 0. Okay, but it is not learning anything. Okay, it is not learning anything. It is just trying to predict either 1 for the entire data set or 0 for the entire data set. So that is my training accuracy is 50% and my test accuracy is 50%. Okay, then I'll be taking tanh activation function in the hidden layers with weights and bias to 0. Okay, you see that I have taken tanh activation function in the hidden layer. Okay, then I have initialized weights and bias values to 0. Okay, I have taken the loss function and optimized it. This part is my training loop and this part is my testing loop, and the same results. Okay, you can observe the same results. Okay, training accuracy is 50% and test accuracy is 50%. Means model isn't learning anything. Okay, then I'll be taking sigmoid activation function. Okay, sigmoid activation function in the hidden layers. Okay, now I'll be doing the entire same part, and you see that my training accuracy is 51% and test accuracy is 47%. Okay, means model is just, okay, it is not learning much, but just it is doing some random guessing. Okay, so that is why I got around 51%. Okay, now when I see the final model weights and bias, these are the final model weights and bias values. You can see that from the feature 1, what are all the weights I have got the same weights. Okay, from the feature 2, what the weights I have got the same weights. Means how many hidden units you add in the hidden layer, it is considering it as an perceptron. Okay, how many hidden units you add in the hidden layer, it is considering the entire model as perceptron. Okay, so that is why the weights and bias values are same. Okay, the weights and bias values are same for the entire model training. Okay,
let us see our second case where we initialize our weights and bias values to some non-zero constants. Okay, in our case 1 we have initialized to 0 values. Now we will be initializing our weights and bias values to some non-zero values. Okay, that is weight values I'll be initializing to 0.5 and bias values I'll be initializing to 0.5. Okay, all the weights in my neural network. Okay, all the weights, that is W111 or W112 or W121. So all these weight values are initialized to 0.5. And all the bias values like B11 and B12 are initialized to 0.5. Okay, now when you compare this case with our previous case where we initialize our weight values to 0 and bias values to 0, you can see a similarity that all these weight values in this case are initialized to 0.5, but in the first case as well we have initialized all the weight values to 0. Okay, now in the case 2 we have all the weights are equal, and in the case 1 we have all the weights are equal. Okay, in the case 2 we have initialized all the bias values are equal, and in the case 1 as well we have initialized all the bias values are equal. So now what happens is there will be similar behavior. Okay, there will be similar behavior of case 2 with respect to case 1. Okay, how case 1 has behaved with respect to sigmoid activation function, there will be same behavior. Okay, there will be same behavior of case 2. Okay, there will be same behavior of case 2 with respect to sigmoid, relu and tanh activation functions. Okay, now let us see an example. Okay, now let's say we are taking the same same hidden units. Okay, that is z11 and z12. Okay, z11 is equal to x1 w111 plus x2 w121 plus b11. z12 is equal to x1 w112 plus x2 w122 plus b12. Okay, this is the output weighted sum of this node. Okay, of this first hidden unit, and this is the output weighted sum of this hidden unit. Okay, now this is z11 and this is z12. Okay, now when you keenly observe z11 and z12, x1 values are equal. Okay, x1 x2 are always equal as they are from the data, so they are constant values. Okay, now when you compare these weight values, they are initialized to 0.5. so this w111 and w112 are equal. Okay, this w121 and w122 are also equal, and bias b11 and b12 are also equal. So as all these values, okay, as all these parameters in z11 and z12 are always equal, z11 and z12 are also equal. Okay, z11 and z12 are non-zero. Okay, are non-zero numerical values and are also equal. That is z11 is equal to z12. Okay, now let us consider relu activation function. Okay, now when you consider relu activation function, relu of 0 comma z11 and a12 is equal to relu of 0 comma z12. Okay, now as z11 is not equal to 0, it is a greater value which is greater than 0. Okay, as we initialize weights and bias values to some non-zero value which is greater than 0, so this a11 will also be equal to z11, and this a22 will also be equal to z12. Okay, but we have seen that z11 is equal to z12. So what happens? A11 is equal to a12. Okay, as a11 is equal to a12, the derivatives of a11 and a12, the derivatives of a11 and a12 are also equal. As derivatives are equal, we'll be having the same. Okay, we'll be having the same gradient values. Okay, the four gradient values that we have seen in the previous case, the four gradient values will be calculated. Okay, now in the four gradient values, the three gradient values will be always equal. The only difference comes is the last derivative value. Okay, the last derivative value. Okay, now the last derivative value will also be same as the previous case. Means how many how many neurons may be in the hidden unit. Okay, in the hidden layer, it will be transformed to a single hidden unit. Okay, how many hidden units may be in the hidden layer, it will be transformed into single hidden unit. Okay, why this happens? Because the weight values, okay, the updated weight values are always equal. Okay, the updated weight values in this neural network, okay, the updated weight values in this neural network, okay, the weight values coming from this feature and weight values coming from this feature, okay, are always equal. Okay, these two pairs are always equal and these two pairs are always equal. So once they are equal, they'll be equal for the entire training process. Okay, once they are equal, they'll be equal for the entire training process. So what neural network thinks, this entire connection is a single connection and this entire connection is a single connection. So it assumes the neural networks as in this way. Okay, we'll be having the same problem of not capturing the non-linearity. Okay, the inability of capturing the non-linearity. Okay, this is a linear model. Okay, this is with the case 2.
Let us take our second case where we initialized weights and bias value to some non-zero constant. Okay, that non-zero constant is same for all the weights and bias in the model. Okay, now this is my model. Okay, this is my same model with relu activation function. In this video, I'll be discussing with respect to relu activation function. You can just replace this relu activation function by tanh or sigmoid activation function, and you can observe the model results. Okay, now you can see that I have picked each layer, and the weights and bias connect. I am iterating through the weights and biases connected to the each layer, and I am initializing the weights and bias values to 0.5. okay, 0.5 is the value I have selected. Okay, 0.5 is the value I have selected. You can try out with 0.6 or 0.7. okay, you see that all the weights and bias values are initialized to 0.5. okay, now loss function is BC with logis loss, and optimizer is Adam optimizer, and this part is my training loop, and this part is my test loop. okay, you see that the training accuracy is 50% and test accuracy is around 50%. okay, so the model isn't learning anything. okay, now these are my final weights and bias values. okay, you see that all the weights and bias values are nearly similar. okay, these are with respect to layer 1, and these are with respect to layer 1, and this is with respect to layer 2. okay,
Now, let us discuss our third case, that is random initialization. Okay, this technique is very important because in many artificial neural network trainings, we see that weights and biases being randomly initialized. Okay, now let's discuss this third case in detail. Okay, now this random initialization specifies the weights and biases are random values but not equal values. Okay, weights and biases are random values but not equal values. Okay, now, in this, let's discuss two cases. Okay, in the first case, we'll be taking random smaller weights, and in the second case, we'll be taking random larger weights are initialized. Okay, now let's discuss our first case, that is smaller weights. Okay, now when it comes to smaller weights, how do we actually initialize the smaller weights is by initializing. Okay, while we are trying to initialize some random weights, what we do is we specify a certain range. Okay, now let's say we have specified 0 to 0.01, means all the values of the weights and biases must be initialized between 0 and 0.001. okay, now let's say we have specified 0 to 1, means all the weights and biases values must be initialized in the range of 0 to 1. okay, as we have taken smaller weight values, we need to specify a smaller range, so that is why I have taken 0 to 0.001, sorry, 0.01, means all the weight values will be in the range of 0 to 0.01. okay, now in this way I have initialized smaller weights and biases values. okay, and the second condition is I'll be taking a data set. okay, I'll be taking the data set where all the numerical values, all the numerical values of the data set are close to 0. okay, I'll be taking a case where all the numerical values, I'll be taking a data set where all the numerical values in the data set are close to 0. Let's say in our data set we have 500 features. okay, now in the 500 features, in the each feature I'll be having some numerical values, right? Now all the numerical values in that features must be close to 0. okay, must be close to 0. okay, this is my second condition. okay, these are my two conditions, and now with respect to the two conditions I'll be passing my data into an artificial neural network. okay, it is a 4-layered artificial neural network. okay, now here you see some graphs that these are Gaussian distributions. okay, these are Gaussian distributions. Now what this Gaussian distribution specifies is, now this Gaussian distribution is with respect to input data. okay, what it is specifying is, now all the numerical values in my data set, not all but most of the numerical values in my data set are close to 0. That is why at 0, we have a raising bar graph. okay, now this is what this bar graph Gaussian distribution specifies. okay, now what is this Gaussian distribution? okay, now what this Gaussian distribution specifies is, now when I pass, this smaller weights combined with smaller numerical values, smaller fixed constant values, that is data values, this both get multiplied, right? okay, now in weighted sum calculation I multiply weights with my input data, right? I'll multiply weights with my input data. okay, now I multiply weights that are smaller value and input data that is smaller value. I'll be getting much more smaller value. okay, now when I apply sigmoid or tanh activation function, in this case I'll be getting much more smaller value which is close to 0. okay, I'll be getting much more smaller value that is close to 0. Let's say what I'll be doing is, I have 500 hidden units, right? I have 500 hidden units, so I'll be having many parameters. okay, now x1 w1 plus x2 w2, so on up to I'll be having x3 w, sorry, x500 w500. okay, in this way I'll be having my z, this entire sorry, I'll be having this node output. Okay, this node output, that is Z11. Okay, now this Z11 output can be calculated in this way. Okay, now this entire term is a smaller value, this entire term is a smaller value, this entire term is a smaller value. Okay, now I add this, now when I add all these values, okay, now when I add all these values, what I will be having, I'll be having another smaller value. Okay, I'll be having some somewhat greater value. Okay, somewhat greater value. Now when I pass this from sigmoid or tanh activation function, it will be giving output which is close to 0. Okay, it will be giving us output which is close to 0. Okay, that is what this Gaussian distribution specifies. Means in each hidden unit, okay, in each hidden unit I'll be having activation function output, right? For each hidden unit in this hidden layer, I'll be having activation function output. Okay, that activation function output will be a numerical value. Okay, that numerical values, okay, that numerical values will be most of the numerical values will be close to 0. Okay, that is what this Gaussian distribution specifies. Okay, now in the similar way, here I'll be having the same, here I'll be having the same. Okay, now when this activation function outputs are close to 0, when I calculate the derivative, it will be also close to 0. Okay, it will be also close to 0. Okay, now this is the derivative value. Okay, now let's say this is the derivative value. Now at the time of gradient calculation, that is backpropagation chain rule, I'll be having set of smaller derivative values. Okay, now in the calculation of w new is equal to w old minus learning rate dou l by dou w old. Okay, now at the time of this gradient calculation, I'll be applying back propagation chain rule. Okay, in the back propagation chain rule, I'll be having set of derivative values. Now I multiply each derivative value. Okay, now when I multiply each derivative value, that is each derivative value is a smaller derivative value. Okay, each derivative value is a some smaller derivative value, let's say 0.01 and 0.003. So in this way, each derivative value will be a smaller derivative value. Why? Because my data is smaller and my weights and biases are initialized a smaller numerical value. So my derivative values will also be smaller values. So when I multiply this smaller derivative values, my entire gradient value becomes smaller. Okay, now when I multiply this gradient value with this learning rate, this entire term will be a smaller one. Okay, now when I subtract this smaller term from this w old, this w new will be nearly equal to w old. Okay, this is the problem of vanishing gradient. Okay, this is the problem of vanishing gradient. Okay, when I use, okay, listen carefully, when my weights and biases are initially smaller numerical values, okay, smaller random values, and my data is smaller. Okay, my data is smaller. In both these cases, okay, in both these cases, when I use sigmoid or tanh activation function in the hidden layers, okay, sigmoid or tanh activation function in the hidden layers, I'll be facing vanishing gradient problem. Okay, in case of relu activation function, we'll be facing the problem of slower convergence. Okay, we'll be not seeing the problem of vanishing gradient, but we'll be facing the problem of slower convergence in the case of relu activation function. Okay, this is the case with smaller weights. Okay, now let's discuss our second case where we initialize larger weights. Okay, larger random weights. Okay, now when the weights are larger random weights, okay, now let's say that is from 0 to 1. Okay, I specified the range from 0 to 1, means my weights can be 0 0.5, 0 0.9, 0 0.8, 0 0.7. Now in this case, what actually happens is, okay, in this case what actually happens is, now x1 w1 plus x2 w2, x2 w2, x3, sorry, x3 w3, x4 w4. So in this way I have some weighted sum value. Okay, I have some weighted sum value. Now my x1, x2, x3 are smaller values. Okay, I'll be taking the same case of x data is a smaller numerical data. Okay, when my data is smaller numerical data, but my weights are larger weights. Okay, now when I multiply and add this entire value, okay, entire value, I'll be getting some larger value. Okay, in this case my weights are smaller, so I'll be having the weighted sum value as some smaller value, but in this case I'll be having the weighted sum value as larger value. Okay, it may be either larger value or it may be either smaller value. Okay, it may be this weighted sum value may be entirely larger value, or this weighted sum value will be entirely smaller value. Now when I pass this weighted sum value through relu or a sigmoid or tanh activation functions, what actually happens is I'll be getting the Gaussian distribution in this way. Okay, for sigmoid or tanh activation function, I'll be getting Gaussian distribution in this way. Okay, now what this Gaussian distribution specifies is, let's talk with respect to sigmoid activation function. Okay, now when we talk with respect to sigmoid activation function, as z values are greater or smaller, when I pass this greater or smaller values through sigmoid activation function, the values will be extreme values. Okay, when I pass this greater, okay, extreme greater values or extreme smaller values of z through sigmoid activation function, the sigmoid activation function will be extreme. Okay, it may be extreme 1 or it may be extreme 0. Okay, so that is why the activation function outputs of each hidden unit will be 0 or 1. Okay, will be 0 or 1. Okay, will be 0 or 1. So that is what this Gaussian distribution specifies. Okay, that is what this Gaussian distribution specifies. Okay, now what is the disadvantage of having this type of Gaussian distribution is, we'll be facing the same problem of vanishing gradient. Okay, we'll be facing the same problem of vanishing gradient when it comes with sigmoid or relu sigmoid or tanh activation function in the hidden layers. And when we use relu activation function in the hidden layers, we'll be facing the problem of unstable training. Okay, unstable training. Okay, let's once summarize. When weight values are initialized larger and when the data is smaller, I'll be getting z value that is weighted some value or some larger value. Okay, okay, either it may be larger or smaller value. Okay, now when I pass the smaller or larger value through the activation function, okay, let's say sigmoid activation function, I'll be getting extreme values, or it may be 0, either it may be 1. Okay, so that is what this Gaussian distribution specifies. Okay, now when I now in this case what actually happens is, when I calculate the gradient, there will be a smaller gradient value. Okay, now when I multiply the smaller gradient value with respect to learning rate, okay, with respect to learning rate, I'll be having some smaller numerical value. Okay, now when I subtract the smaller numerical value from the w1, it will be nearly equal to w nu. So that is why, that is the problem of vanishing gradient. So sigmoid or tanh activation function produces vanishing gradient problem, and relu activation function produces the unstable training problem. Okay, what is meant by unstable training? When you use gradient descent algorithm, the steps won't be in this way. Okay, the steps will be larger. Okay, the steps will be larger means updates will be larger. Okay, this is what unstable training is meant for. Okay, now let's summarize the entire video. Okay, so we have discussed our first case where we initialize our weights and bias values to 0, and in the second case we have initialized weights and bias values to some non-zero constant but equal weights and bias values, and in the third case we have seen the random initialization. Okay, now in these three cases we have faced the problem in training. So we have learned that, okay, we have learned that the weights and biases must not be initialized. Okay, must not be initialized in this way. Okay, we need to use some proper technique to initialize our weights and bias values.
Third case, where we initialize our weights and bias values to a random value, but random smaller value. Okay, random smaller value. I'm choosing weights and bias values as random smaller value. Okay, now let's observe the code. Okay, this is my model and this is the weights initialization. Okay, I have selected a certain range over here. Okay, that is minus 0.1 to plus 0.5. So, sorry, plus 0.1. Okay, all the weights and bias values will be initialized in this range. Okay, you can see that the range is very much close to 0. Okay, that is why I have specified random smaller value. Okay, my range is very much close to 0, so all the weights and bias values initialized will be close to 0. Okay, these are my weights and bias values that are initialized randomly. You can see that all the weights and bias values are very much closer to 0, so that is why I'm saying random smaller values. Okay, then this is my loss function and optimizer, same training and testing loop, and you can see these are my model results. Okay, same, my model isn't learning anything, just it is trying to predict whether the entire data label is 1 or entire the prediction is 0. Okay, enter my prediction is 1 or enter my prediction is 0, and these are my final model weights and bias values. Okay, my updated final model weights and bias values are also close to 0. Okay, initially I have initialize the weights and bias values to some smaller value, so my updated final model weights and bias values are also close to 0. Okay, you can observe it over here. Okay, now I'll be initializing the weights and bias values to some larger value. Okay, means I'll be altering the range to some certain larger value, means I'll be taking from 0 to 1, means my model weights and bias values should be initialized between the range 0 to 1. Okay, this is my entire model, and I'm initializing the model weights in between 0 to 1, means I'm selecting the range between 0 to 1. Okay, now these are my model weights and bias values. Okay, you can see that they're larger weight values. Okay, you can see that they are larger weight values. Okay, yeah, these are my larger bias values. Previously we have taken smaller weights and bias values, now we have considered larger weights and bias values. How we have initialized the weights and bias values to larger? We have altered the range. Okay, we have altered the range to some larger value, so that is why we have got this results. Okay, now this is my loss function and optimizer, and these are my final model results. Okay, you can see that 50% training accuracy and 50% test accuracy, and these are my final model weights and bias values. You can see that our weights and bias values are updated to some larger value. Okay, they are updated to some larger value, means that we have initialized to some larger value, and my final weights and bias values are also updated as larger weights and bias values. Okay, these are my final model results. Okay, now by this results, what you can understand is, while we choose any of the case, in these three cases my model isn't learning anything. Okay, in these three cases my model isn't learning anything, so these three cases are wrong way to initialize weights and bias values. Okay, now in the next video what we'll be discussing is, what is the right way to initialize the weights and bias values. Okay, we'll be seeing the different techniques to initialize the weights and bias values. Okay, now I'll be providing the entire code in the description. You can choose different activation function, you can choose different random weight value or bias value, and you can observe the model results. Okay, please try it out. And this is the entire video on weights initialization, what not to do. Hope you like this video. If you like the video, please like, share and subscribe. Thank you.